1. All right, we're recording. So this is the last part of logs that we're going to review before we bust out the calculus. Solving log equations. And again, this might have been some of the pieces that got overlooked or went through very quickly during pandemic math last year. Unless you had Skurhawk with the dual credit. Yeah, woo, woo, woo. All right. So we're gonna solve log equations, all right? Or we're gonna solve using logs. So here we have log base 10, right, of x plus 1 equals 3. So this is a conditional equation. We want to find the value of x, or values could be, that make this true. And we don't want to do trial and error. So algebraically, remember, what we're trying to do is peel back the layers and get at the x. And we do that systematically by doing inverse operations in the reverse orders. The first thing you want to do, though, is isolate the log. Okay? Now, in this case, what does that mean? This is your log term. And it's already isolated, means it's on one side by itself. Okay? So now, to unlog base 10 something, what do we do? What's that? Yeah, we can either exponentiate or we can do that around the world thing, right, that we talked about. So I like to exponentiate. You could do the around the world thing, but the around the world thing is kind of gimmicky, right? I would rather do it algebraically, okay? So if we're logging at base 10, you can exponentiate both sides base 10. And there's a couple of ways to do that. If you want to use what's there, it's okay to do this. It's it looks a little squirrely, right? But now when you put a base 10, you have 10 raised to the this power equals 10 to the third. It looks bad, but it's acceptable. I almost like just rewriting it, okay? So log 10 to the log base 10 of x plus 1, and then we can put the equal sign where it belongs, 10 to the third, okay? So that's just logging both sides base 10. And now look what happens on the left, right? What is 10 to the log base 10 of blob? It's blob. So this gets x plus 1 on the ground floor, and now 10 cubed is 1,000. And now we're back in Algebra 1 land, maybe day 2 of Algebra 1, right? How do we undo adding 1? Subtract 1 from both sides, and we get 999. Now, is that guaranteed to work? Not necessarily. You do want to check, okay? Because there is the risk sometimes of getting extraneous solutions, but that's typically if we turn a linear problem like x plus 1 into a quadratic. But since there are limited domains of logs, right, we can only take logs of positives, it's not a bad idea to check. Let's plug it in. 999 plus 1 is positive. What kind of 1,000? Positive 1,000. So we could just say positive, who cares, right? Positive, it's going to work. If your math is right, as long as it's positive, it'll work. Okay, so there you go. And then we'll smile at the end, right? There we go. All right, questions on that one? Fun, easy, and easy. All right, letter B. Hey, this isn't even a log equation, is it? It's exponential. Now, you can solve some exponentials by the GTBTS method, the getting the bases the same. But look at the base on the left, it's base E. And the base on the right is 14. Do we know how to write 14 as a power of E? No, not really. So guess who comes to the rescue? Natural log. I need to get at the exponent. I need to unwrap the layers. It's currently inside of an exponential base E. So we're going to take the natural log of both sides. Now, is it okay if you do it like this? Squeeze the L in there and squeeze the L in there. No, not at all. I'm kind of okay with the left side, but the right side, what even is that? 14 ln? Is that the start of a strange haiku? I don't know. Doesn't make sense. Let's go ahead and write it in front. It's an operation. Natural log of e to the 3 minus x equals the natural log of 14. And now, what is the natural log of e to the blob? It's the blob. So if you use that rule, you can jump down to 3 minus x equals the natural log of 14. But here's the thing. The log, natural log, can be really helpful even when it's not base e. So let's look at this other other way to get to the same result. When you have a log, remember, you could bring exponents out front. Remember that? Now, when you do that, you would have to put the 3 minus x in parentheses. And now you're left with the natural log of e. And then just to review, remind you, what is the natural log of e to the first? It's 1, right? And then 1 times anything is itself. So you don't have to show that line. If you just know natural log of e to the blob is blob, you go straight to the green line. But that's another way to get there. And now we're again back in Algebra 1, maybe on the last day of school. I don't know if y'all had natural logs in Algebra 1. But the natural log of 14, that's just a number, right? It's just a number. So let's see, negative x equals the natural log of 14 minus 3. And then how do we undo multiplying by a negative? Divide by a negative or multiply by another negative 1. And so you end up with 3 minus the natural log of 14. You see what I did there? Are you okay with what I did there? Yeah. Change the signs on the left and then bury the negative, right? We want to lead with a positive. Lead with a positive. There you go. Now, if I did natural log of 14 minus 3, hang on. I didn't even realize this. Is that the natural log of 11? No? No. Because this is not the natural log of 14 minus 3, right? This is the natural log of 14, pause, minus 3. So just like with like sine and cosine, if you see, or even if you see like one term after a function and there's no parentheses, imply that that's only that first piece that's part of that function, not the second piece, okay? All right, so it's 3 minus the natural log of 14. That's the answer. And it's exponential, so we really don't have to check, because what's the domain of exponentials? All real numbers, right. Now, assuming the math is correct, then the answer should be correct. All right, ABC comes next. Okay, so we're back to log equations. We need to isolate the log. This one's a little bit more meaningful because how many logs do we have? 2, right? So how can we condense 2 logs into 1 log if they're subtracted? Can we factor out a natural log? And that leaves x minus the quantity x minus 1. Is that how that works? To factor out the natural log of x? This doesn't work, right? The natural log is not a factor. Division? Yeah, very good, very good. We're going to use this property right here. We're just going to use it not from left to right. We're going to use it from right to left, right? So when you're condensing, your first step is to bring coefficients up to the top to get -1 or +1 coefficients. And then you can condense. So yeah, that's what we're going to do. We already have 1 and -1. So I'm going to pull out a natural log, but it's not factoring out, right? It's not factoring out. It's condensing it. We're going to pull out 1 natural log. We're going to pull out 1 natural log to the front, 1 only. And the positive terms argument goes in the numerator, and the negative terms argument goes in the denominator. Okay. That's how we condense it. Is that the same, question mark, as the natural log of x over the natural log of x minus 1? No, no, it's not. Okay. When you have the natural log of a divided by b is your argument. That's the natural log of a minus the natural log of b, and vice versa. So when you're condensing, you pull 1 log out front, and then the arguments become the factors. This is entirely something different. You can't really do anything with this. That is what it is, okay? So be careful when you condense. That could be a multiple choice question all by itself. It could be like, condense this, and the answer choice with the 2 logs would be an answer choice. I would put parentheses around that just to make sure it's together. Now, of course, that's just the first step in an equation. That equals 1. And now, how do I get rid of the natural log if he's standing guard in front there? How do I unnatural log something? Exponentiate it, base E. So as we say in the business, we E it, right? We E it. Now you could show it like this, right? Again, you could do that. Or you know what? You don't really even have to show it if you don't want. We don't typically show like when we divide both sides by 3. We typically don't show it if we add 1 to both sides. So let's just do this one in our head. What would E to the natural log of blob be? The blob, which is x over x minus 1. And on the right side, what would E to the 1th be? E. So there is a little bit of peril in doing it in your head because you might do it to the left side and might forget to do it on the right side, right? You might call the right side 1 instead of E to the 1th, right? So that would be the benefit of saying, okay, it's an equation that's conditional. I got to keep the balance, do it to both sides. All right. Now we have, well, how do we solve an equation like this? This is where Algebra 2 taught y'all the wrong way to do it, and I need to fix it. If you have a quotient of 2 variables in Algebra 1, they probably taught you to do what? Multiply both sides by what? The denominator. Or they put that E over 1 and they told you to cross multiply. Okay. That's really not good practice. Okay. Because when you do that, you get rid of the denominator. And the denominator is kind of important, right? Because it has an inherent restriction in it. X can't be 1. So when you do that as a method for solving, you kind of change the domain. And algebraically, does it work out to be the same? Yes. But in theory, should it be done that way? No. So let's do it the right way. The correct way is to get everything on one side and set it equal to 0. If you ever have more than one variable, get everything on one side and set it equal to 0. So new column, yum, we're going to get minus E equals 0. Okay. Now, what do we do from there? Well, we have 2 terms. One of them's a fraction. We're going to get ourselves a common denominator. So with notability, let's remodel. We'll pull that 0 over there. We'll put the E over 1. And now what's the LCM of x minus 1 and 1? X minus 1, right? We need to multiply this one by x minus 1 over x minus 1. Which multiplying E by x minus 1 to get the common denominator, it's algebraically the same as what your algebra teacher told you to do. Algebra 2, whatever it was. And so now I have my common denominator. It's all over x minus 1. And my numerator is x minus E times the quantity x minus 1. And now it's equal to 0. So notice what I've still preserved. I've still preserved the denominator that says, hey, x can't be 1. And now we're at the junction where we can start separating things. We have a single fraction equal to 0. When is a single fraction equal to 0? When the numerator is 0. So really, we should be writing when, although you're not going to lose points if you don't have it, because it's now a consequence of a theorem, right? A numerator, a fraction is equal to 0 when only the numerator is 0. Okay. Now, if you look at what we have on that line right there, that would be the same as if you were to multiply both sides by x minus 1 and then subtract it across. But we've gotten there by a different method. We've gotten there by an honorable method, right? We still have academic integrity. We still have integrity with the equation. All right, now we can solve this algebraically. Remember, E is just a number. So now we're just going to distribute, right? Distribute. So we get x minus E times x plus E equals 0. Now we do have like terms on the left, right? If this were like 1x minus 3x, we could call it negative 2x. But alas, the coefficients are unlike coefficients. So how can we get a single x representative, Ethan, so that we can solve? What's that? Factor it out, right? We've done this before with implicit differentiation, right? With the dy dx, we had all kinds of stuff. So we'll just factor out the x, and that leaves us a what in the first spot. Don't be a pre-cal student. What's left here? A 1. minus E. What do pre-cal students put there? A 0. They leave it blank. They're like, oh, I'm taking the X out. That leaves nothing left. Because when they take it out, they're not dividing out. Things divide out to give you 1. And of course, then we'll bring the E across. It becomes negative E. And we're almost there, folks. We're almost there. All we got to do is undo multiplying by the quantity 1 minus E. And we get X equals negative E over 1 minus E. And that should work. We'll test it out here in a second. But let's say this is a multiple choice question. Is that an answer choice? No, it's not. It probably will not. Right. I mean, if I were making the test, I would not put that as an answer choice. I will make the test. So here's what we could do, right? There's 2 negative terms out of 3, right? Let's minimize the negativity, right? That's what unicorns do. If I take this negative 1 from the top, there's only a single factor, I can bring it out front, which means I can also bring it to the bottom as long as I multiply it through. Or you can multiply by negative 1 over negative 1, which is equal to 1. So this would be equivalent then to positive E over E minus 1. And now of the 3 terms, only one of them is negative, and we've buried it in the back, right? That would be an answer choice, right, Hank?
Yes, sir.
Right. But wait, there's more. Can we split this up and call it E over E minus E over 1? Because that would be 1 minus E. Can we split up denominators like that? No, we can split up numerators, but not denominators. Okay, not denominators. So make things as simple as possible, but no simpler, right? No simpler. So E over E minus 1. Now we got to be careful. If we come back up here, let's look. Instead of plugging it in to see if it works, you can actually find the domain of the function. We have 2 log terms. This term has a domain of x greater than 0. Sorry, oops, greater than 0. And if I set this greater than 0 and solve, that means x has to be greater than 1. If it has to work in both terms, which one of those would be the domain that takes care of both terms? Greater than 1, good. Because everything greater than 1 is also greater than 0, right? But is everything greater than 0 also greater than 1? No. It goes back to why we can't solve, or how I told you we can't solve those quadratic inequalities. Here's 0 and here's 1. If I shade to the right of 0, I get this. And then if I shade to the right of 1, I get this. And remember, it's the overlapping. The one that works is the overlapping interval. So you can do it graphically. So all we need to make sure of is our answer bigger than 1? And is E over E minus 1 bigger than 1? Yeah, it's easy to see because E over E would be 1. And all I'm doing is I'm making the denominator smaller. So a big number divided by a small number should be still bigger than 1. Yeah, yeah, very good. Very good. Okay. God, how much time do we have now? 9 minutes. 9 minutes. Okay. I think I'm going to skip this one, right? Skip. Is that okay? Or do you want to do it? Skip. I want to bust out the calculus. Let's bust it out. Time to bust out the calculus. Okay, so I do have a question real quickly. We were going to get Devin from last year, the BC. We were going to get him a courtesy bust out the calculus shirt.
I can get it done.
Did we order him one? No?
No.
Okay.
I did not get money from
Yeah, we did. He said he didn't pay, but he was ready to pay if we had a shirt, but we don't have a shirt.
So I talked about the plan that we have a plan.
Okay, you have a plan? Can I get in on the plan too?
Yeah, no, I have you in the plan already.
Oh, for an additional one.
Yes.
I need a
Preemptively, you need a size up, so we're gonna.
I need to get a fat guy shirt.
You need a fat guy shirt.
Yeah. And I'd be happy to like recontribute.
Recontribute.
Yeah.
So
I can ask Devin. Let me ask
what size
Devin.
is that?
I don't know. I need to ask him next period. If
that size large, he's size large. So
what if I give you my large, you give him your medium?
I give you an extra large.
There you go. And then we're all good. Yeah. Okay. And then how would the money work? We just give the money to Angeli. I don't know. Okay, well, good. I'll mention that to him. You don't have armpit stains on yours or anything already from working hard in it? Okay. All right. All right. So good. One thing I know about this class is y'all are problem solvers. Y'all will go actually behind my back often to solve problems. Yeah, that's awesome of y'all. Okay. Let's bust out the calculus. Example 6. If y equals the natural log of x, we want to figure out what is the derivative of y with respect to x. That is, what is the derivative of the natural log of x? Okay, so let's go ahead and start. We'll come down here and we'll write our problem. Y equals the natural log of x. Now, I want to know what the derivative of that is. So on your mark, get set, go. Well, it's kind of hard to start on the right side because taking the derivative of the right side requires us to know what the derivative of the natural log of x is. And that's what we're trying to discover. That's like if you don't know what a dog is and you go to the dictionary and you look up dog and underneath there it says a dog is a dog, right? And there's not even a picture. You're like, well, that helps a lot. Thanks, Webster, right? Or Roget or whatever. It doesn't help to define a word with a word. So is there another way to rewrite this and maybe at the same time put it in some terms of something that we know how to differentiate? Exponentiate. Let's do it. Let's do it. You can either convert this using the around the world trick, or let's unlog it by exponentiating both sides. E to the y equals e to the natural log of x. That's really the best way. You don't have to worry about that around the world conversion formula. If it's logs and you want to undo it, exponentiate. If it's exponents and you want to undo it, log it. All right. Now, what happens on the right-hand side? What's e to the natural log of x? X. Good. Same as the natural log of e to the x, right? You compose two functions that are inverses back to back. They undo each other, right? Lefty loosey, righty tighty, as they say in mechanics, right? The nut's back off, right? Put the nut on, take it back off. All right. Now, can I take the derivative of e to the y equals x, Ethan? I know, I can tell. You're doing too much. This is not solved for y, but is that a problem? No. We could take the derivative how?
I don't remember the word, but
Implicitly, right? So when it's implicit, and this came up the other day, so let me kind of show you two options. When it's implicit, you have to demonstrate what you're doing. So you can either do this, take the derivative of both sides with respect to x. This is the proper and formal way to do it. It's the verb, right? D dx of the left side in the front equals d dx of the right side in the front. That's the formal way to do it. But the informal way, but still correct way, is to just put d dx colon, and then behind there, you don't write the original function again. I think Mr. Skurhawk is doing that. I kind of need to fix that. When you do this, the derivative follows immediately, okay? So let's go ahead and finish both veins here. What would be the derivative of e to the y with respect to x? E to the y itself times dy dx times the natural log of e, right? If you want to just go through that in your head, which we don't need, right? Because it's 1, times the chain rule dy dx. Boom. Okay, so that would go over here as well. We would just jump straight to it. All right, and then the derivative of the right side, what's the derivative of x with respect to x? 1, right? So this would equal 1. So those are the two ways you do it, all right? You put d dx in front of both sides, and then you take the derivative on the next line, or you just put d dx, verb, and then colon, and then you're like, here I go, here it is. All right, there's more room on this side, so I'm going to stick over here. Now I have to solve for dy dx, yes? So to do that, I'm going to divide through by e to the yth power. It divides out on this side, and I get 1 over e to the y. So there it is. What's the derivative of the natural log of x? Well, it's 1 over e to the y. Y. is it in terms of y? It started in terms of x, right? And now I have it in terms of y. Oh, is there a way to get it back in terms of x? Yeah, good. E to the y. What is e to the y equal to? It's equal to x. They're the same. So with just a little mathematical sleight of hand, a little substitution, we get 1 over x. And there it is. There it is. Oop. There it is. The derivative with respect to x of the natural log of x is 1 over x. Memorize it. Now, the domains are different, right? Ms. Skurrock and I were talking about this morning. This x right here requires it to be entirely positive, yes? You cannot entertain negative values. So when you take the derivative of the natural log of x, you do get 1 over x, but you restrict it to positive values of x. You always got to maintain the domain of the original function that you're working with. All right. Now, tomorrow we'll try to be more inclusive, right? Wouldn't we like to include more x values? It's kind of a shame that we only get to include positive x values. You know how many students who got to include from the hair fundraising? 19. It should have been 22, but they only had 9. We raise more money than they have kids. That's right. That's right. So anyway, we'll stop right there. Memorize this. Example 7 will start tomorrow. Okay. And thanks, Mr. Thomas, for sitting in with us today.